Hello and good evening, everybody. This is Obi-Wan Pez for Simplex Pachinko. We're going to be talking tonight about series and sequences because it's right at the end of the semester for pre-calculus especially, or my pre-calculus classes anyway. And if anybody has any questions, feel free to interrupt me and talk about something else, because otherwise I'm just going to talk all night about series and sequences. Anyway. Alrighty. So, when we talk about sequences, we're talking about a list of numbers and technically it doesn't really have to be numbers, it could be just any elements inside of any set. However, we much prefer talking about numbers when we're dealing with stuff like this so that we can be able to do really cool stuff like calculations with any particular values in the sequence. So some of the more famous sequences can be, we can have unpatterned sequences. Which would do things like just list off the birth dates of anyone I ask and just put them in the order in which I ask them. We could also take a sequence and say, okay, well, I want the sequence of all we just take like a random data set. And we could take somebody's, or a list of names followed by a list of birth dates, followed by a list of phone numbers. So we could do all sorts of stuff with data sets. These can be sequences and they don't have to mean anything necessarily. On the other hand, the ones that we like to talk about are the patterned sequences. And these come in kind of two styles. So typically we have something that is explicitly defined. And what this means is that the value of the next term, actually I shouldn't say the next term, so the value of the nth term is dependent upon its index only. What do I mean by index? Well, that's just where it is, its position. So its position in the sequence completely defines what its value is. So one example for explicitly defined sequences might be the sequence of all even numbers. So if I let the sequence of all even numbers be a sub n, and we let that be 2 times n. This is going to be all positive even numbers. So the list of all positive even numbers would be a sub n is equal to 2 times n. So what happens is we say that, well, a sub 1 is going to be 2 times 1. A sub 2 is going to be 2 times 2. A sub 3 is going to be 2 times 3. And naturally, this just continues on. So these are 2 and 4 and 6. And naturally, this keeps going on forever, like as far as we want to go. All right, so this would be an example of an explicitly defined sequence where, again, the index of a particular value or index of a particular sequence element is defined by its position only. So we see over here that we can multiply 2 by n to get the exact position. Now, it doesn't have to be this simple. It could be something really complex and big, ugly function. But most of the time, it's going to be pretty functional. It's going to look like some sort of function f of n that we've seen before. So talking about any of the functions that we've ever seen before, linear, polynomial, exponential, log, some sort of combination of like rational functions with exponential functions with polynomial functions, that's possible. So it can happen. Can have literally almost anything you want in it. And the other type is those which are implicitly defined. So in this case, the value of the nth term of the sequence is dependent upon other values of the sequence. Now, I did say previous values in the sequence, which technically doesn't have to be true. So it can be dependent upon any other values in the sequence. So typically, you're going to see something like a sub n is equal to a sub n minus 1 plus 5. And actually, we did see something like this a while back when I was talking about the Collatz conjecture, which was if you wanted to, you could pick any number out in space and plug it into this particular whatever you want to call it. Plug it into this particular piecewise function, and then repeat it. So evaluate this thing on itself, make it recursive, do it over and over and over again, and eventually all Collatz numbers that we found so far, or all numbers that we've ever plugged in to the Collatz conjecture piecewise function, has come back eventually with 1. So eventually it gets back down to 1, and so we have like this branching sequence, which starts wherever you want it to start, and then it slowly works its way back to 1. So actually, let's do that one. All right. A sub n minus 1 over 2 if a sub n minus 1 is even. And then it's 3 times a sub n minus 1 plus 1 if a sub n minus 1 is odd. So it's not, it doesn't necessarily have to be a piecewise function. That might distract somebody, so sorry about that if it does. But the main point here is that in order to find any particular value, we go back and we're going to look at the previous number in the sequence and then say, I'm going to take that number and plug it into one of these two formulas. So if the previous number in the sequence is even, then we divide that number by 2 to get the next number in the sequence. Or if it's odd, then we multiply by 3 and add 1, and then we get the next term in the sequence. So we had mentioned, like, if you start with a sub 1 equals 510. Let's do that, because I hope this doesn't last too long. Okay, then a sub 2 is going to be half that amount because 510 is even. So we plug that into here, we divide by 2, and then we're going to get 255. And a sub 3 is going to be equal to, well, this is odd, so we're going to triple this and then add 1. So we get 766. A sub 4 is going to take this and halve it again. Let's make sure I got the first number right. Okay, cool. All right, so half of 766 is 383. This is odd again, so a sub 5 is going to be take 383, triple it, and add 1. We get 1150. A sub 6 is going to be half that amount. Is 575. Nuts. It's going to last a while, I guess. Uh, 17, 26. Divide by 2. A sub 8 is 863. All right, let's just go a couple more steps. If I'm doing just even, odd, even, odd, even, odd, it's going to keep increasing in value. So this might take a while. But instead, I will just go another couple steps, and then if we're not shrinking back down again by multiple divisions by 2, I'm just going to let it go. So 2590 for a 9, a 10, divide by 2, and we get 1295. All right. All right, so I'm going to avoid continuing this because I don't know how long this is going to go. So this is a Collatz sequence. And it starts with the number 510. So if anybody wants to continue this, feel free. You can also, I might add, use a computer to do it, which would make this go a lot faster. All right, so for implicitly defined sequences, this is just, for instance, a particular implicitly defined sequence. It is by no means the only one. There are an infinite number of explicitly defined and implicitly defined sequences. You can do them in just about any way possible, and some of the explicitly defined sequences can also be implicitly defined. In fact, most. And yeah, if I had a proof, I would be writing a paper about it. I am sorry that you are in immense pain right now. Took me a while to read that. Oh man. So in addition to Collat's sequence, we've also got the Fibonacci sequence, which has to do with the mating habits of rabbits. It was a puzzle solved by Leonardo of Pisa, and his solution for it ended up being, if you started with one baby pair of mating rabbits, and then barring genetic diversity issues, if they were able to mate after 1 month, then what you have is the baby pair grows up and you still have one pair. When the baby pair grows up at the end of the next month, you will have one adult pair and a new baby pair of rabbits, so that leaves you with 2. At the end of that month, the one adult pair reproduces again and the baby pair grows up. So then we have 2 adult pairs and 1 baby pair is 3 total. And then from here, the 2 baby pairs, still 1, isn't it? Yeah. The 1 baby pair grows up into adults. The 2 adult pairs reproduce. So now we have 3 and 2, which make 5. This then continued on. Fibonacci got the values for this. 21, 34, 55. Yeah, that's going to just keep going right off the page. 21, 34, 55, 89, and 144 are the only ones that I care to memorize. And oftentimes you'll see this prefaced by a 0 term at the beginning. So the Fibonacci sequence is an implicitly defined sequence, and you are unable to create an explicitly defined structure or definition for the Fibonacci sequence. Many people have tried over the years. It's just not possible with our current mathematics. So if anybody comes up with it, please publish that. It would be wonderful. All right, the Fibonacci sequence is given as f sub n, the nth Fibonacci number, is going to be given as the sum of the previous 2 terms. So f sub n minus 1 plus f sub n minus 2. Oh man, all sorts of questions tonight. Awesome. Are there infinitely many prime numbers in the Fibonacci sequence? Yeah, that'd be an interesting question to find. Knee-jerk reaction, I would say yes, but of course, you'd have to be able to prove that. It has eluded mathematicians for roughly 1,000 years, so there's a good chance that the explicit definition of the Fibonacci sequence either just involves something that we don't understand yet, or it's a really complicated You have a formula for the members of the Fibonacci sequence. All right. I guess there might be like a gamma function for it that happened to go through all of the values of the Fibonacci sequence. However, I think they're looking for, Jordan normal forms. Haven't seen that one in a while. I mean, that's sort of a lie. I teach differential equations, so it's been a year, I guess. Okay, so the Fibonacci sequence so far has been an implicitly defined sequence, and this is the easiest definition that we have for it at the very least. I will let Immense Pain just come up with the, or type out the formula for this one. Okay, so then if we take these, there are some really cool, interesting patterns and things like that that exist with the with certain sequences. The Fibonacci sequence in particular is an interesting example. If you were to take the ratio of evening bracketary, if you were to take the ratio of two successive terms within the Fibonacci sequence, then what we end up with is 1 over 1, which is just 1, 2 over 1, which is just 2, 3 over 2, or 1.5, 5 over 3, or 1.66 repeated, 8/5, or 1.6, 13/8, or says 1.625, 21/13. All you Coheed fans out there, 21/13. Oh, definitely gonna have to look at that one. 21/13 is 1.615384, and it keeps going on from there. And 34/21. That's off the page now, so. Is going to be 1.61904766, and of course keeps going on infinitely after that. These are rational fractions, so they will repeat themselves after a certain amount of time. But I don't have a repeating part of the decimal here. You can find it. It's easy enough, and I'm not sure that my calculator even has that many decimal places. Yeah, it does. Okay, cool. Okay, so more or less these are repeating about this many terms, after about this many terms. All right. Okay, let's check that out. A sub n is 1 over square root of 5. Now, is this 1 over root 5 and then the parentheses, or is it like 1 over... I mean, I'm assuming that you've at least got good notation, so it's going to be 1 over root 5 times. Plus root 5 over 2. Okay, so phi to the n minus, interesting, minus root 5 over 2 to the n. Well, that's fun. Yeah, let me know if I got some of the notation wrong here, but... Okay. So then you're doing... +1, but... yeah, well, I guess either way, right? So, whichever way you're doing it. Oh, A matrix multiply. I gotcha. Then diagonalize this matrix. Okay. Cool. I'm going to have to share that with my linear algebra people. See if they fall over themselves on that one. Okay. Oh, other way around, right? Vector times A. Oh no, matrix times vector. Okay. Yeah, I'm gonna have to. Oh, quiet contrary. Evening. Hey, so just out of curiosity, where'd you all hear about the channel? Because I think all three of you I have not seen here before. At least not, like, in person. Yeah, I ended up looking up math on Twitch, and, like, there was one person active, and then several other people that were doing, like, just random homework help in the background, and I was like, okay. Yeah, very nice. Thank you. Well, thank you for coming. This is great. I Well, good evening. Hey, if you have any questions, let me know. I'm not necessarily well versed in anything super beyond sophomore level because that's all that my school teaches. But I have also earned a master's degree in applied mathematics, and I can give it a shot if you've got something. All right. Otherwise, I'm just going to keep rambling on about this stuff, and kind of depends on what you all like. All right, so with the Fibonacci sequence, we have here a successive, a ratio of successive terms which starts approaching a specific value. And Immense Pain actually hit on it already with this thing up here. The value that these all start approaching is phi, which is going to be 1 plus the square root of 5 over 2, which is about 1.618. And this goes on forever. Obviously, it's an irrational number, so it's just going to keep going on. Oh, yeah, absolutely. And if anybody is a teacher, I definitely like that, though. Me being a teacher, I could talk shop all night, too. Yeah, go for it. Drop it in the chat, and I will finish up a couple little things here. So my main point for bringing this up tonight was that I started teaching pre-calculus, I don't know, 10, 15 years ago, and somewhere in there. And I had an issue with the book always hitting on coming up with the explicit form for particular types of sequences. And so this was there are two main types of sequences that we can start getting into with a lot of students and saying like, oh, there are really specific patterns that occur when you have what are called arithmetic sequences and geometric sequences. Oh man, Carl. It's been a while. Hang on one sec. I got a book. So, when you start looking at arithmetic and geometric sequences, these are sequences that date back to the ancient Greeks. So, and I mean, that's when it got like formalized and we had the name come up, or they decided on a specific name for it. However, 414. Okay. I don't want to like randomly start saying like you know, the definition of gradient, so make sure I've got the right one in my head. All right, so arithmetic sequences, we're looking back to, you know, way back in ancient Greek times. Um, what they did was, yeah, it's like 2 years ago, it's fine. What they did was they were looking at patterns of numbers where you were taking a specific term, and in order to find it, all you needed to do was take the previous number and add some specific value to it. Or you could look at it the other way, a sub n minus a sub n minus 1. So the difference between any two particular values was going to be a specific constant, so d. We call it d. It's the common difference. Makes sense. So now I will remind everybody that there was no notation back then. It was all just descriptions of the problem and descriptions of the solution. Um, the idea of notation had not really been truly invented until we start getting into the Islamic Empire and Persia is really where like the first major notations were created to say like, hey, we need to really focus in and start saying like, you know, let's replace numbers with some letter, and then it'll just stand for that when we get into it. Hmm. Oh man. Yeah, quadratics are fun too. Um, so when we get arithmetic sequences, we have a common difference between all two successive terms, and really it's any two terms that are of a particular distance apart, regardless of if it's the next term or like 5 out. If it's always 5 out, then those terms also have a common difference with every other term that's 5 out from each other. So we just go with the one term difference because that's just easiest. It's what we always go with. So for arithmetic sequences, you've got this, which again, all you're really looking at is, well, if you notice, this is divided by 1. And really, this is the same as saying a sub n minus a sub n minus 1 divided by, well, what else has a difference of 1? Well, also, the indices n minus parentheses n minus 1 have a difference of 1. First time I saw this, I was like, well, yeah, I guess that's pretty obvious, but, you know, I never actually put it down on paper. The d value here, the common difference between every successive term inside an arithmetic sequence, is literally the slope of a linear function. And again, when I was doing this at some point, I was like, well, yeah, it's the slope, but it didn't quite sink in that literally it was the same way to find the slope with linear functions that are continuous as with linear functions that are discrete or arithmetic sequences. So here we could say that, D is going to be the common difference, which is useful for discretized functions, whereas M is useful to refer to for continuous functions. All right, so then if we're talking just linear functions, well, we could just use a point slope form for this. So what we've got then is that we could take the denominator here and multiply it across. And we could say that this is going to be d times n minus parentheses n minus 1 is going to be equal to a sub n minus a sub n minus 1. And then add the a sub n minus 1 to the other side. So a sub n minus 1. Let's just keep going this way because this will work. A sub n minus 1 plus d times the quantity n minus parentheses n minus 1 equals a sub n. Well, just like with linear functions, it doesn't actually matter which term we're using or what second point we're using in order to find a linear function. So here, instead of using a sub n minus 1 and n minus 1 as my secondary x comma y, what we can actually do here is just say, well, let's let this be any different value. Let's have it not be dependent upon n. Let's have this be a sub k. So a sub k plus d times parentheses n minus k is going to be equal to a sub n. So again, if we think of this in terms of linear functions, this can act the same way, just like with point slope form, as we can for any other point, k comma a sub k, rather than necessarily going n minus 1 comma a sub n minus 1. The pattern has to hold all the way through. The ratio has to be the same no matter which 2 points you pick. So you pick 2 points here and here, or you pick a point that's further along the line there, right? Then those have to have the same slope between all of them. So I much prefer using this one because when my students pick something like, a sub 3 equals 6 and a sub 10 equals 53, right? You don't necessarily have to have a sub 1, which is what the book always wants you to have whenever you're doing the equation. So the book is going to insist that you're like, okay, a sub n is equal to a sub 1 plus d times n minus 1. And it's very prescriptive. You're supposed to figure out this formula right here. No difference. Just this. And I told my students after a while, I was like, no, just do it with this one. Figure out an anchor point. We have an anchor point. It's 3, 6 or 10, 53. Take your pick. It's just like when you're doing point slope form for linear functions, right? So we said, take this. This is going to be a sub n is going, well, okay, d is going to be equal to 53 minus 6 divided by 10 minus 3 is going to be something over 7, 47 over 7. Oh, well. All right, that is not nice, not simplifiable. And then we say that a sub n is going to be equal to, and now we could plug in any a sub k we want. Let's go with 6. Keep with the low number, just because. Plus 47 sevenths times n minus the k value is 3. Or if we felt like it, we could have used the other one. So 53 plus 47/7 times n minus 10. So either of these equations would work just fine for all these two particular values. And again, I don't have to find the nasty fraction that a sub 1 is inevitably going to be. I could just leave it like this. That's fine. Okay. So, curl for vector fields, right? It has been a while. Let's see. Nature and significance of curl will be talked about in section 10.9. Well, I guess I'll go there. Well, it's part of Stokes Theorem. Come on now. Awfully long time, unfortunately, since I have had to deal with curl in any useful way, and even longer since someone explained it well to me. All right, so it's the determinant of the matrix with ijk, the partial derivatives of x, y, and z, and f's. Continuous vectors. Generating functionality. Interesting. Well, I'm going to say that I probably don't understand it anywhere near as much as I need to if I were to try to explain it. However, let's see. Physical meaning of curl in fluid motion and circulation. That seems reasonable. so SR0 is a circular disk of radius R0, center P bounded by circle. Let F be a continuously differentiable vector function in a domain containing this thing. Alright, do the Stokes Theorem, do surface integrals, all that good stuff. Curl of F times the normal times normal at P, which is the center of that circle. Yeah, all I can tell right now is that this is basically telling us what the circulation of this particular like fluid is. And so like in order to figure out what the, don't quote me on this, but in order to figure out, I'm going to totally delete the video on demand. In order to figure out the circulation of the fluid within a certain space, you need the curl to be able to tell you how it spins. So it seems like this is sort of inherent to the vector field. Anybody can correct me if I'm totally just talking out my rear here, but that's what I'm getting out of it. So apologies if that's not right, but yeah, that's about all I can come up with in the like without actually looking it up. I think so, but the problem is that this is also then a fluid field. So typically like you're dealing with fluid dynamics in this sort of mixture, whatever it is. Uh-oh. Oh, there we go. Okay. Started doing all sorts of fun stuff there. Yeah, some number of weeks ago, I also did immense pain. Some number of weeks ago, I did Taylor series, which has always been just a wonderful, fascinating thing for me. Uh, somebody said like, "Oh, you know, you can generate any function you want based on a Taylor series," and I was like, "You can what now?" Hold the phone. Are you in fact serious that I can literally, well, okay. You can create almost any function. All right, that's fair. Yes, yes. It can't go, it can't have, certainly can't have any discontinuities, or if they're discontinuous somewhere, then they're finite and reasonably, yeah. Okay, so I did the same thing for geometric sequences for my students, and I said, all right, this is going to be a sub n is going to be a sub n minus 1 times a particular common ratio. And so here, this is going to be a sub n over a sub n minus 1 is going to be equal to any r value, or a constant r value. So this was, again, where I said, well, it doesn't have to be the next one over. It can be further ones on. But again, every time that you get an a value at the bottom here that is further away, you have to multiply by more r's to get to a sub n. So as it turned out, we said, well, if this is 1 here, then this could be a sub n over a sub n minus alpha equals r to the alpha. So then I said, all right, we can move this over again and just have it, well, start with this thing. So then this is going to be a sub n is going to be equal to a sub n minus alpha times r to the alpha. And then I said again, we can let this be if we let alpha be n minus 1, then we could let this be a sub n equals a sub n minus a negative 1 is plus 1, so that's a sub 1 times r to the n minus 1. And this is the typical one that everybody goes with again. But if you let alpha be just, what is it, m minus k was the one that I always do, then we end up with a sub n is equal to a sub n minus n goes away, minus a negative k is a sub k times r to the n minus k. So again, my favorite way of doing things, pick any two values that you want here, and it doesn't have to be any particular two values. So these are a little nastier because if you pick something that isn't nicely divisible, it gets kind of gross. And this is not going to work nicely, but whatever. Can do I really want that? No, probably not. Meh. Yeah, actually, this one's easy. This is nice. So if we have two like this, we can end up with a sub n is equal to, well, actually, right. So if we do a sub 5 over a sub 3, this is going to get us r to the, you can subtract those values, and so this is going to be 2. The problem here with r squared is that this creates another problem. Potentially r squared could be either r squared is going to be equal to 9. So then r could potentially be either plus or minus 3, which usually we can kind of decide that, you know, it's going to only be positive, or we can have negatives as well. Most of the time they won't give you one that are only, or an example that's only 2 away, because they want to avoid this kind of issue right here. So a sub n is equal to a sub k, again, could be 6 times, we'll go with 3 to the n minus 3 for k, or a sub n equals 6 times, that's not 6, 54 times 3 to the n minus 5. All right, so we could use the one with r equals -3. It's just not typical. So you will see it occasionally, but All right. All right, let's see what you got. X0 is greater than 0. Then define x sub n plus 1 to be equal to x sub n times the quantity, 1 minus 1 over 2 to the n plus 2, x sub n greater than x sub 0 over 2 for all n. Well, that sounds interesting. So, geometric algebra or geometric calculus? We already have algebraic geometry. Now he wants geometric algebra. Oh, man. Do you know particularly what it was talking about or dealing with? It's not a constant value, so we can't do anything fun with that. Man. You know what kinds of So I'm interested to know if this has anything similar to do with like rotors, because I feel like, I mean, this could be completely off topic and not. My problem is that I haven't done analysis or any of the like, uh, major math classes that you're supposed to be taking in like your junior, senior year of college. I mean, I took a lot of them, but the ones I took were mostly focused on like, God, what did I take? Abstract algebra, history of math, uh, how to teach math. Like I had an ed degree for my undergrad, so I had a lot of that. And then my graduate, I mostly focused on differential equations. So I still didn't do a whole lot of still didn't do a whole lot of analysis. All right, induction, huh? Well, It's always possible. So x sub 2. I guess we're showing it for n equals 0 first. So x sub 1 is equal to x sub 0 times 1 minus 1 over 2 to the second power. So this is going to be 1/4, it's 3/4, so x1 is going to be 3/4 of x0. Unless I copied that wrong. Oh no, greater than. Right, we're good. My other problem is I haven't done this in years. So might also be interesting to look into lean. I don't know if it would be able to do this, but could at least get you some framework for how to set up the induction and then be able to prove the induction. Hopefully we'll be able to do some of this. Now we got to use this one. Okay. So anyway, if we were to do x sub 2, that's going to be equal to x sub 1 times 1 minus 1 over 2 to the, that's going to be 1 plus 2 is 3, right? So this is going to be 7/8 x1, which is equal to 7/8 times 3/4 x0. Okay. So now this also might be interesting because all we really need to do is find the product of all of these individual values. So it's what we're going to get. It's 1 minus 1 over 2 to the n plus 2. Starting with n equals 0 and going to infinity. All right, well, there you go. Gee, that simple, huh? So really, you need to prove that this is greater than 1/2. See, I have reduced your problem. Now it's easier. Right. Yeah, that's about right. Oh, man. And as a mathematician, I'm done. So, well, that's the question is it? So I think you have to, yeah. Oh, does that turn it into a sum? Oh, goodness. Logs 1 to 1, so we're good on that one. Oh, I guess. Shh, look at you trying to make things easier. Yeah. Ah. So the infinite product got you 0.577? Wait a minute. I know that number. Oh my god. Yeah, oh no, it's totally worth trying to solve it. Um, that's a fun number. Let me guess, 0.57735026919, right? If that's it, then yeah, we okay. Oh well. You said 0.577, I got hopeful. Um, yeah, that value was the square root of 3 over 3, which would have been wild if that was actually the right number. All right, so here, so the product of all these things, we're taking the log of a product, so it's going to be the sum of the logs of the individual things. Definitely catch me out if I'm making that up. And then the sum of a bunch of logs. Those are not particularly nice or anything. If we factor this out, then we're left with 2 to the n plus 2 minus 1. This is probably going nowhere, but worth a shot anyway. That's just going to be minus 1, so. Yeah, I mean, like, I'm probably not coming up with anything useful here, but can we use any of the, y'all tell me here, can we use any of the log rules? I mean, not the rules, but the summation rules from Calc 2. Prove that it actually converges first, and then see if we can find a bound on it. Oh, don't tempt me. I mean, it's probably not solvable, but it's still a very interesting problem to look at. So, quite, I think you're missing a negative. Yeah, okay. There you go. Yeah. Yeah. Sum and goes from 0 to infinity. Negative parentheses n plus 2. No, this is fine. We're trying to figure stuff out together, so I mean, this is technically this is research. So, all right, then 2 to the n plus 2 minus 1. We want to figure out if that's greater than negative 1. Now you've got an infinite series of something that's outside of. Oh man. something that's outside the log now. We have an infinite series. So then this is essentially going to be like infinity minus infinity. So we'd have to, ooh. I had a thought. Oh no. I had an evil, evil thought. So we're trying to find the limit as k goes to infinity of the sum as n goes from 0 to k of negative n plus 2 plus log of 2 times 2 to the of 2 to the n plus 2 minus 1. You may or may not like this. So this is an arithmetic sum, and this is non-arithmetic, as far as we can tell. But there might be a way to simplify this overall. And if we can simplify this, this turns this sum into the limit of something as infinity subtracts infinity, which is prime territory for L'Hopital's rule. It's an evil, evil thought, but it might work if we can somehow turn this into something that's not inside of a summation. Yeah, so let me see. This is the limit as k goes to infinity of this part, the infinite sum of negative parentheses n plus 2 as n goes from 0 to k is totally finite. How dare anyone suggest otherwise? So the first one is when n equals 0, we get a negative 2. Plus, the last one is when we get k, or n equals k. So this is going to be a negative parentheses, k plus 2, all times k plus 1, all divided by 2. Yeah, infinity minus infinity is an indeterminate form. So I don't remember which one it was, but there was an example in the calc book that I have, which is currently holding up my monitor. There is an example where you use infinity minus infinity, and you can actually turn it into whatever other L'Hopitals you were required to use in order to get it in the proper form or whatever. So yeah, that's the first one. And the second one is going to be n goes from 0 to k. Log base 2 of 2 to the n plus 2 minus 1. other indeterminate forms such as infinity minus infinity. Yep. Okay. So, oh, can sometimes be evaluated. Okay, so it looks like, yeah, no problem, immense pain. Um, I don't know. We might be able to push this a little bit forward on video on demand, so hope to see you around again. And yeah, look for me on social media. I am Obi-Wan Pez, and this is N Simplex Pachinko. So, uh, see you around. Hope you have a good rest of your week. Good luck out there. And goes from 0 to k of log base 2 of 2 to the n plus 2 or minus 1. All right, so then we could shift the negative out, and then we get, I keep doing that, n equals 0 to k, log base 2 of 2 to the n plus 2 minus 1, all right, minus k plus 1 times 2 plus k plus 2, so, okay, k plus 4, all divided by 2. All right, so let's see. If we can turn the 2 all right, maybe not. Yeah. Okay. So it says that other indeterminate forms may be used, such as infinity minus infinity, provided it can be turned into a quotient, which then behaves the same way as the regular L'Hopital stuff. So you got to turn it into a quotient. And in this particular case, we have constants in our denominators. So that's, yeah, it's probably not going to work, actually. That's too bad, though. Mm. Oh well. And like technically, if we kept it as it was, right, all the way at the beginning. Anyway. Well. All right, well, quiet contrary, you have any other questions? We can maybe extricate ourselves from this one, because I'm not sure that this is going to go anywhere, unfortunately. Man, I really want it to now. I'll take fake ones too, that's fine. So this is just Microsoft Whiteboard, which has Some easy tools at the bottom. It just has like the standard 4 colors of pens, and then it has this like rainbow and a galaxy pen. Just changes colors as you go. Highlighter, eraser, a ruler, which is very useful, I must say, because I can draw actual straight lines instead of the BS that I try to do. Uh, and then if I want to select like something in particular, I can also lasso around a particular thing and move it around. So I find it helpful. It's way better than in like 99% of its functionality. It is way better than the one I use during the daytime, during my day job, which is Zoom. So no offense to Zoom, you know, they do a good job, but mm, it's falling just a little bit short of like MS Whiteboard. Um, I much prefer the style here, and and the other awesome thing that happens is sometimes Zoom will. There's a very long explanation as far as that's concerned. Oh man. Yeah, so I tried sharing the MS Whiteboard like from day one, and I much prefer that. But the problem was that when I tried to do that, my students couldn't actually see where my cursor was. So actually, you can't see where my cursor is right now either. But the reason is like I'm right next to the plus or minus 3 here. The reason behind that is because I'm not actually focused on this screen. As soon as I drop this in and click on this window, now you can see my cursor. Uh, the Zoom whiteboard did not do that. So when I was using Zoom, it was focused on Zoom and not on the whiteboard. And then when I tried to like change which window I was focused on, it would constantly just mess it up and hide my cursor. And I'm like, so I'm talking to my students. I'm like, yeah, this thing over here. And they're like, what are you talking about? I'm like, right here, the thing. And they're like, I can't understand. I was like, this right here. And they're like, oh, yeah, I see that. But I can't see your cursor. I'm like, oh, okay, there we go. Yeah, it was it was an experience. We may or may not, yeah, we may or may not be able to have that fixed at some point in the near future. Yeah, it's only really good in the sense that I can like do a couple of things that I need on it. There was something that I needed to do recently on whiteboard, and I was like, oh, I wish that functionality was added in, but it's like one thing. 99% of the time, I'm usually on Zoom saying I wish that it had the functionality of MS Whiteboard. So, like I said, it might be fixed now. Oh, that's fine. Yep. So I am a college level professor. I hesitate to say professor, but I'm a college level teacher at a 2-year school in the Mid Atlantic region of the United States. So, for the most part, I teach pre-calculus, and occasionally I've been doing Calc 1, differential equations, usually one per semester, or at least one class per year is like our basic algebra, algebra 2, that area. Um, And this next semester, I'm going to be teaching for the first time our like fundamentals of mathematics class, which involves a lot of probability statistics at very, very extremely basic levels, combinatorics, you know, the fun stuff that you practically never get to do when you've got to prepare students for calc. Um, and then also, yeah, it's like mean median mode, like not even distributions, but doing data set stuff. So what I'm actually planning on doing at some point is bringing in the there's a there's a really mean trick. Um, so Darren Brown did this one. If you know Darren Brown from the UK, he does all sorts of cool stuff, including he said he was going to take, he had somebody flipping coins. And like they would take turns flipping coins, and they would have other people rotate out just to make sure it wasn't like it's just Darren messing with stuff. Like, no, no, no. It's really like it's all these people. So he said, okay, I want you to pick a combination of three coins. So the guy's like, okay, heads, heads, tails. And Darren says, okay, well, I'm then gonna pick, what was it? I think it was, oh, nuts. I forget what it is now. Anyway, I gotta look it up again. Um, I think it was you take the middle one, change it, and bring it to the front. So it would be tails, heads, tails. No, that's not it. What was it? You want, I think you want, or maybe it was just, I think it's send this one, send the opposite of this one to the front, and then shift everything down. Leave this where it is also. So it's, you want tails, heads, heads. Because by the time heads and heads pops up here, you've already won. Like 99% of the time or something like that. So and the trick of it was that as soon as he hit tails, heads, heads, note that there's a 50-50 shot of the other guy getting a point too. But what he'd do is he'd say, "Oh, everybody celebrate. Yay." And then they'd say, "Okay, start over." And so and so it was like the what he was doing was trying to say, there's kind of there's like a force behind community thinking where like we can get everybody behind it and everybody rallies behind Darren and says, "Yay, it's gonna work." And of course, Darren's gonna win 90 whatever percent of the time. But it's really because he's interrupting the sequence and doing the sequence break and says like, "Oh, too bad." Right? You're not going to have another combination of heads and heads that's going to pop up first before Darren's does. Because if you end up with, like, yeah, in order to have two heads in a row and be ready to have a tails at the next one, you had to have had at least two heads after a tails. Like, it's almost guaranteed. I think it's the only time that he can actually win a point if Darren does his celebration and then starts over. The only way that he can actually score a point is if they flip heads, heads, tails first. Like, so it's a 1 in 8 chance right off the bat of being able to do it. Otherwise, you're going to flip a tail at some point and then you're going to hit two heads before you get the next tail. So yeah, that's what it is. you copy the opposite of the second one to the front. Yeah, so so I think I'm going to bust that out at some point during the semester and be like, now let's think critically about this. What is actually going on? Because I really like, I really like making these students especially think because they're like, "Ah, I hate math. I don't want to do this. Why am I here? I'll just take the lowest number course, which of course does not mean it's the easiest one. But they see all of the here are all of the classes that you can choose from to take one of your my favorite concept. Oh man. So this gets really tricky because like there's I think differential equations is probably my favorite class, like overall the entire class to teach, mostly because of the students' attitude, but also because of um, just there's so much little cool stuff to throw in there, and the students are just like, where's this coming from? And then you break it down and smash it into bits and show them where it all comes from. But yeah, individual topics, that becomes so hard to do, to like break down. So I do like teaching a couple of them because I've invented stuff that comes out of this. So one is absolute value. And I've done this before on this channel. You could see it on my YouTube or whatever, but I might as well just bring it up again. So my absolute value problems. I was encouraged at one point to start on a project-based learning initiative. So try to get like a bunch of projects that students would be able to work during class. And it turns out that it's like a lot of fill in the blank, which I don't really enjoy. Um, but like it it got me to do this thing, like writing out all of the things ended up getting me to learn about this concept. And then I was just like, that's kind of amazing. I hate doing it, but at the same time, it'll work. So when you're doing absolute value problems, you're saying that this is going to be a yeah, I hate doing fill in the blank stuff. It's not even a chart. That's the problem, is that it's like a sentence that I'm trying to create. It's guided notes. And like they don't want to be there for that. So so anyway, absolute value, you break it down and you start saying this is the same as talking about the distance from a particular target value. Now, normally, if you're just talking about the absolute value of A, you're saying that this is a distance from 0. But if you think about it, right, it doesn't have to be from 0. How do you figure out the distance between any two numbers? Well, the distance between any two numbers is what you get when you subtract them. And so you'd say like, okay, your x is going to be the value that you have minus the t is going to be the target value. So this is your target. And then again, we don't really care whether this is positive or negative. We just want to know what the distance is. So this is where the absolute value stuff comes in. And then really, you could also say, instead of doing that, you could also say, if it was, if x is greater than t, then we do this. If t is greater than x, we do this. And this now becomes a piecewise function, absolute value x minus t. As long as up here, again, x is greater than t, and here x is less than t. And then here you can also say, okay, which one's bigger? And then when is it equal? Well, if it's equal, it doesn't matter which one you do, so usually we just do this one by default. So absolute value is really a distance from a target value, and again, whichever one is bigger is the one you put in front. And that's your piecewise function. At this point in the semester, I've already talked about piecewise functions and how how piecewise functions work, where you put them in, stuff like that. So then here, what I said was, okay, if you've got a particular absolute value function and you want to figure out when when the distance between these two numbers is equal to 3, right? And I'm going to generalize this even further. I'm just going to let it be d. When is the distance between these two objects equal to d? Okay, well, this means that I have a particular target value t that is on a number line. My x value, I have no idea where it is. It's my variable. The t value is a constant, and the d value is a constant, which we can go, again, the distance is exactly d that our x is away from t. So we can go d in the upward direction and get a particular value, or we can go d in the lower direction and get a particular value. When you do that, now you've got down here, this is t minus d, and this is t plus d, and these are our solutions. So what does that mean? Well, it means that x is equal to t plus or minus d, or you could go through a whole bunch of stuff. Anyway, doesn't really matter. The more important part was once we extend this and say that, well, I don't want the distance to be exactly d. What if the absolute value of x minus t is less than d? So this says that we can use the same picture. So here t minus d, here t plus d. I'm still going to get those 2 points as my border points because this is the maximal distance that we can travel. Well, if this is the maximal distance we can travel, that means that the acceptable values are going to be less than that away. So they have to be within these distances. And since it's not equal to, we can't be at those locations. So you shade this in between 2 open circles, which says that x is then going to be between parentheses, or interval, open interval, t minus d to t plus d. All right, what about x minus t being greater than d? Well, same thing. You draw the same picture. You got x, you got t, you got d in the upper direction, you got d in the lower direction. That leaves these 2 locations. You can't be at those locations, but you must be further away. So if I'm further away, that means that my solutions are out here. So what is that? That's x must be between negative infinity and t minus d, open, union, open, t plus d to positive infinity. Where's the tedious algebra? Right? I just did it in general. I didn't even need necessarily to have like particular values in there. This just right? And when they can actually figure this out in groups, and like when they can figure this out in groups by themselves, this is really awesome because they can discuss how it all works and like understand, hopefully, what all the little nitty-gritty pieces are. Now the other piece of this is like I extended this even further. Well, I mean, I use specific examples, and I said, what happens if we have a different transformation for this? So if we have like the absolute value of 2x plus 3 is less than or equal to 7, okay, what am I subtracting? Right? You need to subtract 2 things in order to have a difference or to have a distance between 2 things. So here we're subtracting 2x and negative 3, and it's less than or equal to 7. So the target value is now negative 3. and our variable term is 2x. The distance maximally can be 7, which gets us values downward at -10 and upward at +4. Matthew or what? Welcome. So, pretend that those are equal. Equal distances. All right, so we said that here we can be at this distance. We can go exactly a distance of 7 away because it's equal to. So we'll go here, and we'll go here. And then when you go to these two locations, now those are the border points. We're allowed to be at the border points. And now you say the distance between these objects must be less than or equal to. So it must be closer to -3 than either of the border points. So therefore, shade in between. Now, this is not the right answer. This is not done because we weren't looking for 2x. We were looking for x. What are the values of x where this works? Well, literally divide everything by 2. What do you get? You get x here. You got 2, -3/2, -5. These are solid circles at the borders and shaded inward. So x has to be between a closed -5 to a closed closed +2. There's a solution for that one. Where's the tedious algebra? Yep, quiet contrary. Have a good night. Now, if you like the tedious algebra, what I tell my students is that you can't just go through and say the thing your teacher taught you to do, which is make 2x plus 3 less than or equal to 7, and then 2x plus 3 greater than or equal to -7. Yes, technically that's true, but everybody keeps screwing this up. Everybody messes this stuff up. Those two things right there, the sign and the sign on the 7. Yeah, and that could also work. So what I tell my students is that they're not allowed to do that. All right, they are not allowed to just use whatever their teacher taught them. What they have to do is use the actual definition of the absolute value. So the actual definition of absolute value of 2x plus 3 was that we wanted, yep, so this is 2x minus parentheses -3, really. So absolute value of a number is the distance from 0. But the absolute value of like a set of numbers, so I define this up here, right there, as being you want the distance or the difference between two numbers. So you want to find out how far away these two numbers are. Because really, your absolute value of A isn't just the absolute value of A. Your teachers have lied to you. It is the absolute value of A minus 0. So you're trying to find the distance between 0 and A. And I don't necessarily fault your teachers for lying to you because, again, this is for simplicity in terms of like not trying to confuse you and stuff like that. But eventually it does catch up. Eventually it does confuse people to not understand the deep meaning of these mathematics. And in fact, the much easier meaning of these mathematics. Yes, the absolute value just means the distance from 0. But you can do this again right here. And you see it in your physics class too. When you're doing percentage error, right? The percent error is equal to the absolute value of actual minus experimental over actual. You see it right there, right? You are just saying, I want to know how far apart these are. I don't care which one's bigger than the other. I don't care which one's positive or which one's negative. What I care about is how far apart are they, and then when I divide by the actual, I'm getting a percentage, which is positive, which is always positive. So here's the thing, right? The idea was, what if a is a negative number? So if a is -2, -2 minus 0 is still -2. We don't want a -2. We want to say it's just 2 away. So by saying it's 2 away, or in order to say it's 2 away, you have to say that the -2 minus 0 has an absolute value. And that absolute value is positive 2. Oops. All right. So, going back a little bit, just because you weren't here for the very beginning of it, the absolute value of x minus t. So you're subtracting two numbers. It really needs to be broken down into a piecewise function, which is either x minus t, which you just do as subtraction, provided that x is the bigger number. So if x is the bigger number, or potentially equal to, then we do that subtraction. Otherwise, oh, you can't see it, sorry. That one. You just do x minus t when x is greater than or equal to t. Then if x is less than t, then we do the opposite subtraction, t minus x. Why? Well, it gets you the same value, it just switches the sign of the result. So t minus x is going to get you a positive result if x is less than t. So you decide which one you're going to use on this depending on what the values of x and t are, which one's bigger, all that good stuff. Down here, what I said to my students is that you are no longer allowed to just do the thing your teacher taught you where you get greater than or equal to -7 on the right. Can't do it. Don't do it. I don't want to see it. So what I said was, if you're going to do this, if you're going to do it algebraically, you have to do it right. The left-hand side of the equation is going to become 2x minus a -3. You are subtracting or trying to find the distance between 2x and -3. When you do that, you're either going to get 2x minus -3 if 2x is greater than or equal to -3, or you're going to get -3 minus 2x when, or if, 2x is less than -3. That's really what we're getting. And here you didn't necessarily have to literally swap them. You could actually just say that this is the same as negative parentheses 2x minus a -3. So negative on the outside of that parenthesis. So then here what happens is we get 2x plus 3 is less than or equal to 7 because, again, absolute value of 2x plus 3 could just be 2x minus -3 is 2x plus 3. And the other one we can get is negative parentheses 2x plus 3 less than or equal to 7. Note, this does not change. This does not change. Right? This stuff over here does not change. We are only changing the definition, or rather what we see in front of us, of the absolute value term. We're changing absolute value into its broken up pieces. We're not going to change anything else in the entire equation. That's it. Then when we do this, yes, you distribute. This is going to be a -2x minus 3. It's less than or equal to 7. And the way that I do this is I say I'm going to make my x's positive because I don't want to have to deal with changing the sign around. I don't want to have to deal with dividing by negatives on an inequality. So here I'm going to add 2x to both sides and subtract 7. This gets me a negative 10 is less than or equal to 2x. Divide by 2 is negative 5 is less than or equal to x. Now, if you want to know what that is the other way around, all you have to do is literally swap it in a mirror. So this is going to be x is greater than or equal to negative 5. All right, whichever one of those you want to use. And over here, we're missing something. So you could do the distance between 0 and 2x plus 3. Right? So that is just telling you that the distance between 2x plus 3 and 0 was going to be a positive number. So that's it right there. Over here, this one is telling you that the distance between 2x plus 3 and 0 was a negative number. And so when you take that negative number and you take the absolute value of it, you take the opposite of what is here. I don't like doing that because you're taking an extra step. I mean, maybe I'm taking an extra step by doing the whole plus turns into a minus and negative, but, you know, whatever. All right. So absolute value 5x minus 7 is greater than or equal to 12. I'm going to continue this, but that's going to be our next one. So here, 2x plus 3 is less than or equal to 7. We're missing a word in between these two things. And what's going to happen is we're going to get to the end. We're going to come up with two separate inequalities, and we're going to have to combine them because this is a... So I don't do that. I don't use the distance from 0. I say that it's the distance between the two objects that are inside the absolute value directly. It no longer needs 0. You don't need a 0. So I read this as the distance between 5x and 7 is greater than or equal to 12. But yeah, you can, I mean, you can use yours. It is mathematically correct. It's just that you have to be careful about how you're doing it. All right, so then here, solving algebraically, we're going to subtract from 3 from both sides. We get 2x is less than or equal to 4. Divide by 2. And x is less than or equal to 2. So x is less than or equal to 2. X is greater than or equal to negative 5. There is a word that must go in between these every single time. It is a logical conjunction. You must either have an and or an or statement connecting these two things. Now, how do you know which is which? Well, if you graph these, you'll figure it out pretty quick. You got negative 5 on the left, positive 2 on the right. X must be less than or equal to 2. So, less than or equal to is a solid dot shaded downward. X must be greater than or equal to negative 5 is a solid dot at negative 5 and shaded upward. If we say or for this, either x must be less than or equal to 2 or greater than or equal to 5, then we notice that we are going to include every single possible number on the entire number line. Which means that not only will negative 5, 0, 1, 2 work, but so will 3, 4, 5, negative 10, and negative 500,000. If you try to plug those numbers in, however, you are not going to get a number that is less than 7. Those numbers on the outside. It's only going to work if you get the numbers on the inside here. And therefore, we can only use an AND statement. So it must be both of these statements which are satisfied. So it must be an AND statement. And once you do this, you should immediately go back and place it up top if you haven't already. If the distance must be less than the two, or must be less than a certain value, then it's going to shade inward and you must have an AND. If the distance must be greater than a particular value, then they're going to be shaded outward and you must use OR, because OR statements collect all possible solutions. AND statements only look at the overlapping solutions. So if you were to do, for instance, this one, if you do this as an AND statement, you'd end up with two separate pieces, which are completely disparate from each other, and you'd have no solution. Here, however, we get x must be between -5 and 2 inclusive on both sides. Okay. So for this one, right, the absolute value of 5x minus 7 is greater than or equal to 12. I'm doing this graphically myself. Uh, 19/5 works, but negative 19/5 does not. So the critical points that you're looking at are when the inside of the absolute value. Yeah, no. So the point here is that the inside here must have a value of 12. Well, if it must have a value of 12, what numbers have a value of 12? That's either going to be 12 or negative 12. Yeah. Then you add 7. Yep. So again, my preferred method for this is to use a graphical method wherein you say that we are subtracting or trying to find the distance between 7 and 5x. 5x, we don't know where it is. That's our variable term. It goes on the number line itself. 7 is going to be our target value. And then the distance, we said the critical points or border points are going to be at 12. And then the distance must be greater than or equal to 12. So we are allowed to be at that particular location, or we are allowed to be further away. If we're further away, we then look for what are the values that we were looking for here. This is 7 plus 12 is 19. 7 minus 12 is -5. And this is 5x. So if we want to simplify this and just make it x, then all of our terms in the entire diagram get divided by 5. So a distance of 12/5 from 7/5 is going to get us an upper bound of 19/5 and a lower bound of -5/5 or -1. We're still solid at the outer points and then shading outward from there. So then x must be from -infinity to -1 bracket union bracket 19/5 up through infinity. So, like, what's confusing about it? Jousting, huh? So that's just to get like the most basic example. If you just have the absolute value of 3, this is asking you what is the distance that 3 is away from 0? Why is it away from 0? Well, that's because when you try to find distances, distances between any two numbers, you're going to look at A minus B. So here, here the distances that exist, we're looking for this value, whatever it ends up being, A minus B. It's going to get us the total distance between these two objects. If we look at this, 3, we're allowed to make this 3 minus 0 without any sort of cost, right? 3 minus 0 is simplifiable to 3, just as it is. Yeah. So you got 3 intervals going in between. Sure. So then here we say, well, let's do it with this. Say it's A minus B to find the distance between these two objects, A and B. Then, again, we didn't care what direction we're going in. So, if x is bigger than t, we're going to subtract x minus t. If t is bigger than x, then we're going to subtract t minus x. It gets you the same number, but it gets you a different sign out front. If you just like swap the numbers and don't change anything about them. So if we did, 3 minus 0 versus 0 minus 3, both of them are going to get you 3. It's just that one of them is in the positive direction and one of them is in the negative direction. So if we make A and B a little more complicated, A is going to be 5x, and B is going to be 7. Then we're looking for what is the distance between these two objects, 5x and 7. We know that it has to be more than or potentially equal to 12. Okay. Do you understand that the distances between two numbers is going to be represented by their subtraction, their difference? Okay. Okay. So the distances between two numbers, A and B, is going to be represented by their difference, A minus B, unless B is bigger. I mean, technically, that's the distance, but it's going to be a negative number, right? Which are in opposite directions. So it's telling you, really, 1 minus 4 versus 4 minus 1 is telling you that it's that size, but what direction it's in matters. What absolute value is telling you is, I don't care what direction it's in. I just want to know how far away it is. So, for instance, like, I want to know how far away Columbus, Ohio is from Boston, Massachusetts, right? Like, I don't really care what direction it is. It's vaguely east to get to Boston from Columbus. But what I want to know is, like, how far do I actually have to travel? So that's what absolute value really is don't tell me what direction I'm going in. Just tell me how far away this thing is. Is my car going to make it on a certain amount of gas/electricity? You know, yeah. So A and B are just going to be arbitrary numbers. So pick A, pick B to be some numbers that are off in space. Doesn't matter what they are. If A is bigger than B, then A minus B is their distance. If A is less than B, then their distance is going to be represented by B minus A, because again, distance is considered a scalar value. It doesn't include direction. We only care about the size of this number, the size of this difference. How's that work? I mean, yes. So my whole shtick is really that I'm going to go back and I'm going to look at this in terms of I'm going to look at this in terms of, like, where did this concept even come from in the first place? And that's pretty much everywhere, everything that I do on this channel. Um, it's going to be like, let's define this thing. Oh, by the way, we need some notation for it. What have people used in the past? So yeah, it may also have not helped that you came in right at the tail end of the thing. So like, where are you getting this stuff from? That doesn't make any sense. Of course it doesn't, because you weren't here at the beginning. So don't feel bad. Yeah. So if A is greater than B, we got A minus B. If A is less than B, we got B minus A. That then becomes a piecewise function where we are going to use this and say that the absolute value of A minus B is going to be given as this piecewise function. This is how you do algebra on absolute values. Yep. Yeah, and it also didn't help that I had this word salad over here of just so much stuff. Let's go clean. Start over. Yeah. So if you use the definition of absolute value, or what I insisted my students do, is anytime that they use absolute value algebraically, they have to use these statements. They have to use the piecewise function statements so that they can show me that, yes, I really understand what it is you're talking about here. They were not allowed to fall back on just what their teacher taught them. Hey, Quiet, welcome back. All right. So yeah, this is where I sort of invented this graphical method for solving absolute value inequalities, especially, but equations work too. Um, so that students can kind of understand the concept that I was trying to get up top, which was that we're looking for really where are we're talking about distances in terms of absolute value, and then are we closer or further away from this target value than this distance? In this case, our target value is 7. We need to be further away by a distance of 12. So 12 or further. So start at 7, go 12, and then go further. And then here this was 5x, so divide everything by 5. Okay, well, let's look at this one algebraically before we jump too much into it. What I would recommend is that when you look at doing it algebraically, again, we're saying that you could do this as the piecewise function. 5x minus 7 is greater than or equal to 12. And again, we already discussed this in terms of the stuff we saw here. These are necessarily going to be separate from each other. So this is going to have to be an or statement. Okay, so 5x minus 7 is greater than or equal to 12, or negative parentheses. 5x minus 7 is going to be greater than or equal to 12. And where that comes from, again, is our b minus a. However, this b minus a can be rearranged as negative a plus b, or negative parentheses a minus b. So I'm choosing this one when we're doing all these. So here, make it negative parentheses 5x minus 7. And then multiply this out. So 5x plus 7, negative 5x plus 7, greater than or equal to 12. Add 5x, subtract 12. And here we get a negative 5 greater than or equal to 5x, 5 by 5. X is less than or equal to negative 1, or negative 1 is greater than or equal to x. Read it either way. Or add 7 to both sides. 5x is greater than or equal to 19, divide by 5. X is greater than or equal to 19/5. Or x is less than or equal to negative 1, which again, negative 1, 19/5, shade, shade out. And when we look at the other side over there, we got the same picture. So negative 1, 15, 19/5, shade outward. All right, and then regardless of what we're doing here, one of the other types would be something like the absolute value of 3 plus 7x less than 1. Now for this one, again, if you're going to do it graphically, using my method, I'm not going to tell you to try to do this and make it a minus negative 7x. This is terrible. Anytime that you get a negative variable term, you're going to have to do all sorts of nasty stuff to the graph. So don't do that to yourself. Instead, what I would do is rearrange this so that this is now the absolute value of 7x minus parentheses negative 3 less than 1. keep the variable term positive. So if that means that it's already positive here and you want to make this a minus a negative, don't do that. Move it. Swap the locations and make the other one a minus a negative. And here in this case, this is going to tell you that the distance between some unknown 7x and the value negative 3 is going to be no more, in fact, less than 1 away. So 1 in either direction is going to make a negative 2 up or a negative 4 down. The distance, that subtraction, must be less than 1. So the total distance must be closer than these borders. So we shade in between. Must be closer than the borders, so we have to shade in. And then here, this is again 7x, not x. So we have to divide everything by 7. So this is negative 2/7 with an open circle and shaded inward. This is a negative 3/7. We don't technically need to write this because it's just a solution. We get a negative 4/7, open circle shaded inward. And again, we don't need the distances up top, but might be worthwhile. So these are a distance of 1/7 each. So then x must be between open negative 4/7 to negative 2/7 open. Oops. I'm in the way. And then algebraically, right? If we want to do the algebra for this, then we're going to do the same thing we did up top. The subtraction, as it's such as it is going to be 3 plus 7x is less than 1. It's just literally whatever we had up top. We are less than or equal to, so our border points, we must be closer to the target. Therefore, we have an overlapping region, and then it continues on beyond that. We don't want to include all real numbers, so it's just between the two, so it's just where it overlaps each other. So we get an AND statement. And up top, or rather over here, we discussed that this would just be negative parentheses, 3 plus 7x. All right, quiet contrary, see you later. Good luck out there. And again, try to get 7x by itself. So here, 7x is less than 1 minus 3. 7x is less than negative 2, divided by 7. X is less than negative 2/7. And on this side, we've got negative 3 minus 7x is less than 1. Add 7x, subtract 1. We get negative 4 less than 7x. Divide by 7. Negative 4/7 is less than x, or x is greater than negative 4/7. When you combine these two together, negative 4/7 is down here, negative 2/7 is up here. We are starting from open circle at negative 2/7 and shading downward. We're starting at negative 4/7, open circle and shading upward. And it's an AND statement, so it's only where they overlap. So, middle stuff. Absolute values just in general. I was a part of the New England Math League when I was in high school, and we did the NEML, which was 6 questions, approximately once a month, and highest score got all sorts of fame and among the math nerds. But yeah, the one that they always did every single time. Current year, powers, sum them up, get the current year. So add up the, and then find A plus B plus C, I guess minimum. Find the minimum A plus B plus C. That can work. I always hated these questions because I was just like, I don't really understand what I'm doing here. It's not awful, but it's pretty awful. For a bit. If you have any particular questions, definitely. But though I did forget my water somewhere. Get that later. Any other topic I want? Oh man. uh Is there any particular topic that you don't really get? Let's put it that way. Any level. Doesn't matter, as long as I've actually taken that course and So I'm oftentimes they can do infinite series. Obviously, it can't be literally infinite, otherwise it would take literally an infinite amount of time. But they can at least find something accurate to like 12, 13 decimal places, which is beyond the tolerance of the calculator. And once it gets beyond the tolerance of the calculator, it just shuts down and says, cool, that's close enough. So 13, roughly 13 significant figures, depending on your calculator. But yeah, they can use infinite series. They can also use they can also use linear approximation, which is fun. Um, I mean, the calculators don't, because literally it needs to be accurate to 13 decimal places or whatever. But like if you wanted to just take like the square root of 6, right? You wanted to find as accurate as you can, as fast as you can. What you'd actually do here is say that we want the function, the square root of x. We're going to plug in 4 and get 2 as an output. So really, it's going to be 4, 2 as an input-output pair. And then we can approximate it as y equals m times x minus x1 plus y1. Y is equal to, m is really f prime at x1 is x1 plus y1. Y is equal to the function. So if f of x is equal to the square root of x, then f prime at x is going to be equal to, nope, 1/2 x to the negative 1/2. So this would be 1/2 times x1 is 4 times x minus 4 plus y1 was 2. This is going to be a half of yeah, 4 raised to the negative 1/2 is going to be a half. So then this is going to be 1/4 times, this is 6 minus 4, the intended input, 6, plus 2. So that's going to be 2 over 4 is, oh, shoot. There we go. 2 over 4 is a half, plus 2 is 2.5. So there you go. 5/2 is going to be approximately equal to the root 6. Obviously not terribly accurate. I have probably 4 math notebooks that are running right now. I have 2 of them that actually have like research or something that I'm working on in terms of like trying to teach stuff. And then my other 2 are just going to be like my starting to get my classes into a formalized notebook, which of course is pointless because it changes every single semester, but not the point. What were you thinking? Yeah, so like one of them, or the other 2 are like more formal, and it's trying to like get down what I want for my classes. And I mean, like I said, it changes every semester, so it's kind of like it's sort of pointless, but at the same time, I just really need to keep everything digitally and like be able to go back and alter and change and whatever. Yeah, I mean, this is pretty good. We can literally just keep this going. I guess for me, saying how would you go about multiplying a circle and a square would really depend on what do you mean by multiplying. So do you mean like areas, perimeters? Do you mean, measurements of them, or multiplying the shapes themselves, which I think is where you're going with this? In which case I would love to hear what you mean. Okay, yeah. All right. Yeah, so it's an extreme distribution is really what you're doing. Hmm. Every point, you say. Literally infinite. Yeah. So if I were actually to replace every point in a square by circles, radius which way? Here or here? So radius as in literally half the side length. Yeah, inscribed, okay. So this means R needs to be outside as well. And then as we go over here, this be these points here. So then you're going to get this shape. Oops. Essentially, yeah. No. Okay. I was just trying to say, like, if we tried to, like, bring it up into a, if this was a net, would that work to bring it? But it doesn't work as a net, so, oh well, it's fine. Ajab TW, how you doing? Probably mispronounced all sorts. Anyway, yeah, so if you do a circle, and then from every point you build a square off of that. This would start going around. How does that work? Oh, right. And then the top here. Need that. Right, because the corner follows the same rule. Yeah. Okay. 2R in any direction here. Yeah, alright. Seems to work. Well, I'd say we're doing pretty well tonight. Mostly working on pre-calc type stuff. And if you have any questions, feel free to ask. Yeah, I bet. So closed figure A and B will have the property that A star B is equal to B star A defined as such. Can you prove it generally? I mean, it should. But saying it should and saying yes, it definitely does are two different things. So in this particular case, you would have to show that any point x comma y in your plane, in your shape 1, multiplied by any particular point in your other one, x2, y2, or what have you, would end up yielding the same points, whether you did it one way or the other. Yeah, Ajab, this is, sorry, if you prefer to be called something else, let me know. So this is a bit of stuff that Matthew was working on for just for fun. It's trying to prove how to multiply shapes, if you will. Well, when I refer to fun, it usually means not for a class, but hmm. Yeah, and those are usually the most fun problems to work on. It's the ones that you don't have to work on. Hmm. That seems really messed up. Just trying to like trying to find the inverse of a particular um, yeah. Yep. Ajab, do you have anything in particular that you'd like to look at? Let me know what type of concept you're looking at, and I'll see what I can do. Right. Yeah. Certainly, division is not associative when talked about that particular way. Yeah, if you get a good abstract algebra book, there's some things to look at in there in terms of understanding why multiplication and division are actually not the same operation. I mean, they're literally the same operation, but at the same time, anyway. Yeah, it's been a while since I've said that one. I guess that might have been last week. It's been such a long time since last week. Oh, man. The end of this semester is absolutely killing me. So when you're doing associativity of multiplicands, or of the inverse terms, 1 over b and 1 over c, you're fundamentally doing something different than when you're saying, I'm going to divide. Because division is a binary operation, just the same as multiplication is. So it requires 2 inputs to get some output. But your inputs for each of the associative pieces are different. Like fundamentally, they are different. Because when you're doing association with multiplication, you're saying I'm doing a times 1 over b times 1 over c versus a times 1 over b times 1 over c. This gets you a over b times 1 over c. This gets you a times 1 over bc. If you're trying to do it on division, yeah, it's going to be, there you go. Yeah, if you're trying to do it on division, then this creates the problem where you're saying, I want a over b over c, which gets these things to be like yeah, you're ahead of me on that one, so yes. Yeah. Constant of proportionality. So that depends on what you're thinking of or what property we're trying to use here, but I think what you're looking at correct me if I'm wrong here, but I think what you're looking at is direct relationships. So if you're saying like x is directly proportional to y, then I should go the other way. No, that's right. Yeah. X is directly proportional to y, then what you're saying is that y is going to be allowed to be equal to some constant, let's call it a, times x. So I think where they're going with this is the constant of proportionality should be this a value that's stuck up front. So it's even better than slope, because in this particular case, what they're saying is that this is directly proportional. So if you just have an x value, you just have to multiply it by some number, your constant of proportionality to get y. Like if you're just saying, oh, well, they have equal slopes, the problem is that you've got the possibility that there are parallel lines. And parallel lines don't have a direct relationship. On the other hand, something that is directly proportional to another goes through 0, 0. And then it has some sort of relationship like this. So it's always going to go through 0, 0. And then some point out here, normally we just call it xy. However, on this particular graph, this might be, for instance, x comma 3x. Nope, other way. Eh. X comma 1/3 x. We'll just do that. That's fine. So some random point on the graph is going to be like x comma 1/3 of x, because our y value is going to be 1/3 of whatever our x value is. So then we know what the slope is. That's going to be just 1/3. Let's be. So we replace the y in the coordinate with 1/3 of x, and now you've got an actual relationship that you have there. So if you're looking on it on a graph, you're basically working backward. Is that you'd say, if I have this graph, it has to go through the origin point, so we know it's going to go through 0, 0. And if it went through, I don't know, 5 comma 17, right? Something that's not nice. Then what we've got here is in theory, you could use the slope and just find, m equals 17 minus 0 over 5 minus 0, which is 17/5. Right? In theory, that should be your constant proportionality. The other way to look at it in this particular case is that since it goes through 0, 0, and since our x and y are going to have a direct relationship to each other, that you could also say that this is going to be y divided by x. So if you were to shift all of your variables to one side, y over x equals 1/3. Here in this relationship, y over x is 17/5. All right, does that work for you? All right. Anything else? All right, so because they are so interrelated, I'm going to send everybody over to raid Jason Charles Miller, who is a very fine musician. He plays a whole bunch of different genres. I think of him mostly as rock. He does some country stuff too, but like he kind of transcends all labels. Yeah, you got it. Okay, so we are going to raid Mr. Jason Charles Miller. He's a great guy. So if you're at all interested in his music, it's definitely a great person to listen to. And I've got a few other people who are really awesome. If you're not really interested in his music, we have Edriosa, who is doing Resident Evil Village. I almost guarantee Jason Charles Miller will raid her as soon as he's done. And Alex Ward 777, who is an actor and he's playing Vampire the Masquerade Bloodlines. Um, Alex is, if you've seen like creepy things in almost any movie recently, there's a good chance it's him, especially since he's very tall and thin and can really look creepy. So anyway, we're gonna go see Jason Charles Miller and see you all next time. I will be back on Friday for a gaming stream. Lately, I've been doing. Um, lately, I have been doing. Um, nuts. What am I doing? Lately, I've been doing Control and also Astroneer and Noita, which is a Finnish game in which you have magic wands and blast things, and it's randomly generated procedural stuff. Anyway, I hope you all have a good week. Well, 2 days anyway until I'm back, and another week until I'm back for math. So, have a good one. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.